So, we have already started talking about cross correlation function, right. So, that is something we have already done. So, what we will try to do now, we will get some more property of this cross correlation. Okay. So, we have defined two things, one is cross correlation and then we have given a property of joint stationarity. Okay. And then we have said what is the property when two signals or two random processes will become uncorrelated, we have given that. Okay. The next part of definition is when two random processes, we call them again by definition, they are incoherent, okay, or we should say orthogonal. Orthogonality in deterministic signal we have already seen. Now, let us see for random process what is the definition of orthogonality or incoherency, both are interchangeably used. So, I have already told it must be, if it has to be incoherent or orthogonal, it must be first uncorrelated. So, therefore, I must have this property. Okay, so this must be there. Now, among them, if one of them is 0 mean, okay, either x bar is 0 or y bar is 0. Okay, if that happens, then this happens to be 0 and those signals are generally termed as incoherent or orthogonal. Okay. So, this is just by definition. So, we are just defining different kind of signals that we will be encountering. Of course, accordingly that R x y, that joint correlation will have its own definition, okay, or cross correlation will have its own definition. So, we are just defining them. So, we are saying that if R x y tau is just it is, or R x y t comma t plus tau, it is just function of tau, then we say it is jointly stationary. Okay. If R x y tau is equal to x bar dot y bar or x bar into y bar, then we say it is uncorrelated. If R x y tau equals to 0, then we say those two signals are incoherent or orthogonal. Okay. So, that is by definition. And then because we have this, we will also have a corresponding power spectral analogy. Okay. So, similarly we can actually put a cross power spectral density. It is again by definition, it is just the Fourier transform of this one, right. So, we call it SXYF, which is just nothing but limit by definition t tends to infinity. You truncate, because the basic definition is you truncate the actual signal if it is autocorrelation or autocorrelation and its own power spectral density, then it is just XTF mods square, right. But here because two signals are there, so you first do for the first signal, okay, and then do for the next signal and do a time means do a ensemble average 1 by t. So, that is the definition of this one, and if you take this definition again go through the same process of Wiener the way we have proven Wiener-Khinchin theorem, you will be able to show that R x y tau, as long as they are jointly stationary, we will be able to prove that they are Fourier, these two are Fourier pair. Okay. So, this is something we will be able to show that, and similarly we will be able to also show that R x y tau is a even symmetric function. Okay. So, that will be but when we say even symmetric, it is something, there is some hint into it or some trick into it, it becomes R y x minus tau. Okay. So, we are not proving these results, it can be done similarly. Okay. It is not very complicated, the way we have proven that, similarly you know the R x y tau definition and you just put the things, you will see that this has to be the case. Okay. So, that must be the case, and immediately by taking this relationship we can also show that R S x y f must be equal to S y x minus f. So, this directly comes from there. Okay. So, these are the property which are for two different random process and they are correlated or cross correlation, we can get these properties, okay, cross power spectral density or cross correlation. Okay. Now, with this let us try to see if I have a signal or a random process which is just a summation of two random processes. This is going to be very important because I might have whenever we are receiving something, I might have one random process which is associated with the signal itself and another random process which is actually associated with the noise, and most of the time my channel is linear. So, as long as it is linear, definitely the overall signal I will be getting, that will be just addition of these two. So, that is why it is called additive channel. Okay. So, whenever I will be receiving something, I can always by the virtue of this concept that the entire channel is linear. So, I will be able to say that it is just additive, the noise will be added on top of that signal. So, two random process often in my receiver will be added. So, I need to also see how do I characterize that. Okay. So, if I wish to characterize, a random process can be characterized by its autocorrelation function. So, I need to evaluate R z tau, okay, which is nothing but z t plus tau ensemble average. We have the definition. Now, z t you replace by x t and y t. So, x t plus y t and x t plus tau plus y t plus tau, right. The first term will be x t plus tau, and this, because it is ensemble average, it will be distributed over the addition. So, it should be x t plus tau ensemble plus there will be another term related to y. So, y t plus tau. That is where you will see that why that cross correlation is so important. Here that term will be coming out. So, you will have a multiplication with these two and you will have a multiplication with these two. So, x t y t plus tau and y t x t plus tau. So, this is nothing but the autocorrelation function of x. So, I can write that as R x tau as long as my x and y are all wide sense stationary at least. So, it will be just dependent on tau. This is also same thing. So, I can write if these two processes x and y are jointly stationary or jointly wide sense stationary, then I can write this as R x y tau, and this will be R because y is taken first. So, that should be y x tau, right. So, that is something what we are getting. Okay. Now, let us start putting all those assumption or all those definition that we have given. So, suppose the process is just not jointly stationary, these two processes, they are also uncorrelated, then immediately what will happen? This R z z will be R x tau plus R y tau plus this should be x bar y bar, this also should be y bar x bar or x bar y bar, that is same. So, that should be 2 x bar y bar. Okay. Now, if they are incoherent or orthogonal, and that must be 0. So, I get R x tau, put tau equal to 0, what do I get? For remember whatever we are doing, that is for incoherent, okay, or orthogonal system. What is this? We have already proven that should be the power. This is what happened for a signal which is incoherent or orthogonal. Okay. If two signals, two input process are incoherent or orthogonal, most of the time this is what is happening. Okay. Your signal will be probably, even if signal does not have a 0 mean, your noise definitely will have 0 mean. So, we have told that, and they will be actually uncorrelated, Okay. So, that is always true, signal cannot be correlated with respect to noise and noise cannot be correlated with respect to, they have different source where they are getting created. So, they cannot be correlated. Okay. So, if that is the case, then they will be definitely uncorrelated, and even if your signal, that depends on how you are transmitting, if that is not having 0 mean, but your noise will definitely have 0 mean. So, we have told that it will be incoherent if one of them are having 0 mean. So, immediately I can say that noise plus signal which is coming to me in the receiver will always be incoherent or orthogonal. So, I can always write this. So, therefore, I can always write, that is a very fundamental thing, that for our analysis we can always very safely say that as long as they are stationary and uncorrelated and all those properties holds, I can always take the overall power that I am receiving, it is just addition of noise power plus signal power. This we take as assumption, but this is the fundamental basis behind it. It happens because of these things. If they were correlated, if they were incoherent, I could not have written this. So, you have to be very careful whenever you are putting this formula. You have to also check whether all the assumptions that we have already stated are valid for this system. As long as they are valid, you can take this assumption, otherwise no. Okay. So, this is something you should always remember. Okay. So, now we are almost in the mindset or framework to now analyze. We have already analyzed the low pass noise. Now, in receiver you can always see there are two ways the receiver can function. One is I am transmitting baseband data, okay. Then probably it sits around 0, the frequency component that is there, suppose voice, I do not modulate, I just transmit it as it is. Then probably it will be around that 0 and I have to employ a low pass filtering. So, the noise that will be there in the channel or at the receiver, it will just go through that low pass filter only. Okay. So, that case low pass filtering version of noise is good enough. But when I do modulation, what I will be doing? I will be translating my signal, I will do modulation, we have already seen that is just translating to a higher frequency. So, I will take that entire band and put it in a higher band, and at that point if I wish to reject some amount of noise, what I have to do? I have to employ a band pass filter. Always you will see your receiver will start with a band pass filter. That serves two purposes. One is, of course, it gives you the rejection of all other signals. You just want to get your own signal, so it just rejects all other signals, that is the first thing. Second thing is it also rejects most of the noise out of band, which is not inside your band, because inside your band you cannot do anything, noise will be added with your signal and you have no way to separate them out if you are not doing digital processing. Okay. As long as signals are analog, you have no way to actually suppress them. But what you can do outside the band where you are not interested, just put a band pass filter, it will reject all the noise, the way we have seen for low pass filtering that happens. So, that way any receiver, if you have a modulation, always will start with a band pass filtering, and the noise that comes, that goes through that band pass filter. So, we have to first characterize what happens to the noise if it passes through a band pass filter. So, that will be our next target. Okay. So, let us say I have a noise which is a band pass noise, okay, whose spectrum looks like this, it is similar, sorry. So, that is 0, that is Fc, that is minus Fc, this is that 2B, that is the bandwidth, okay. And because the noise was flat, so this particular value is eta by 2, whichever was there. So, same noise, same power spectral density, it is, we are still assuming that it is flat over the band of our interest, okay. So, it is still remaining flat, it will probably drop some other frequency, some other very high frequency, but not in the band of our interest. So, as long as we are taking that assumption, the noise, band pass noise will look like this, okay. And associated to that, this is the spectrum. So, associated with that, I will have a noise equivalent random process. This xt, I will now say something and then we will prove that this is what can be done. that this x t, whenever it has a characteristics of this one, that it is a band pass noise, can be represented as this. Where x c and x s will later on prove that they are uncorrelated, incoherent random process. So, they are actually jointly, of course jointly stationary, that is the first thing. They will be uncorrelated to each other and they are incoherent to each other. So, we will prove this. Okay. So, these two are two separate random process, x c and x s. This is called the in phase part and this is called the quadrature part of noise. Whatever I have written, I have not proven that. Okay. So, we will try to prove this, because then what will happen, any noise that comes in, once you pass through a band pass filter, you will be able to write it this way. Okay. And that will help you, because you will also get the property of these two things. Okay. And that will actually help you, will in the process will characterize both of them. Okay. X c and x s, what is the associated autocorrelation function, what is their cross correlation function, and then what are the relationship between them, as well as the power spectral density. So, we will characterize everything, but we are saying that x t can be represented like this, okay, where omega c is related to this f c, 2 pi f c. Okay. So, this will be always possible. So, let us try to see what are these things. So, for that I will draw one circuit, okay, just to prove this. You will see, you will appreciate after I analyze this, but initially just take the circuit as it is. Okay. So, there is a multiplier. So, x t, whatever the input signal I have, which is a band pass signal, right, it exists in a band. I multiply this with 2 cos omega c t plus theta, where theta is a known random variable. Okay. I get a 1 over here, I pass it through a ideal low pass filter of frequency response HOF, where HOF looks like this. It is ideal filter from minus b to plus b, transfer function is 1. Okay. I pass it through it, I call this as B1, and then I again multiply this with cos omega c t plus theta. Remember, I am just creating a hypothetical circuit, but this circuit is realizable because these two are having same phase, that means it is means actually generated through same oscillator. Okay. So, that is possible in a circuit. Further, this is C, I have a adder over here which creates D, and the other arm I will have similar multiplier, but now I will be multiplying with sine. This will be A2, again a ideal similar low pass filter which has same transfer function. This will be B2, another multiplier where I multiply again with the sine, add these two and I get D. Okay. So, I can write D as yt, that is my output. So, what I will try to see is the transfer function of this particular system that I am creating. Okay. So, I will first try to evaluate what is the transfer function of this, then you will understand why I am doing that, all those things will be very clear. Okay. So, I am just first trying to get the transfer function of this whole system. How do I get a transfer function? I first need to get the impulse response of it. So, basically I excite this with a delta t and try to see what will be the corresponding output. And when creating this transfer function, I have to also make sure that this is linear time invariant. So, therefore, what I will do, instead of just putting a delta t, I will give a delay to that delta. Okay. So, basically I will put a delta t minus alpha. Okay. So, I will just give a delay, so that I want to test that at output it is just a delayed same amount of delay to the output, it is just function of that entire t minus alpha, that is what is happening. Okay. So, that is something I want to test, then it will be linear time invariant. Okay. So, let us try to characterize this whole thing. So, at A1 what do I get? I have a delta multiplied by cos. So, any function multiplied by delta, it will just pick the functional value at that point. So, if I am multiplying delta t minus alpha, that means at t equal to alpha it will pick the functional value and it will put a delta function only over there. So, therefore, it will be, if you see over here, A1 is nothing but this cos this multiplied by delta t minus alpha. So, therefore, it will just get multiplied and t will be replaced by alpha. So, I will just get A1 as 2 cos omega c alpha plus theta delta t minus alpha, right. This is what I should expect at A1. Similarly, A2 must be 2 sin omega c alpha plus theta delta t minus alpha, right. So, these two things I get. So, A1 A2 I have got. Now, this is just a delta function pass through a, if I just again come back to the same picture, this A1 passes through a ideal low pass filter which has a corresponding transfer function as h0 t. So, a delta function now is the input to a h0 t. What do I expect at the output? It should be convoluted with h0 t, and h0 t convoluted with a delta function must give me the same function. We know that any function convoluted with a delta will give me that same function. Okay. So, therefore, if I just try to calculate B1, that must be same, this is a constant for it, right. So, 2 cos omega c alpha plus theta, and now delta will be convoluted. So, it should be h0 t minus alpha. Similarly, B2 should be 2 sin omega c alpha plus theta delta h0 t minus alpha. After that, what we are doing? So, from B1 and B2 we want to get C1 and C2, then add these two we will get YT, right. So, what is C1? That is just multiplication of this, and C2 is just multiplication of this. So, therefore, overall D if I write, that is nothing but this h0 t minus alpha will be there in both the cases, t minus alpha. I will have 2 everywhere. So, 2 I can take out, and this is nothing but cos omega c alpha plus theta into cos, it will multiply by omega c t plus theta plus sin omega c alpha plus theta into sin omega c t plus theta, right. See why I have created that whole circuit, because I wanted a cos A minus B formula, nothing else. This whole circuit was created because I wanted that cos A minus B. Okay. Why cos A minus B? Immediately you can see, if I just do cos A minus B, so it will be omega c t plus theta, theta gets cancelled, it will be just omega c t minus alpha, h0 t minus alpha into cos omega c t minus alpha. That makes it a linear time invariant system, because it is just a function of this yt what I get, because I have put a delta with a delay of alpha, then what do I get? It is just function of that t minus alpha. So, the entire thing gets similarly delayed, right. So, it is time invariant. So, I could prove my point by that. Okay. So, overall if I just say that my yt, if I just excite it with delta t, it should be 2 h0 t into cos omega c t, right. I can just write this. When I put delta into it, so that must be my impulse response therefore, because I have put delta t as my x and I have got this. So, what is this? This is nothing but, let us try to just see, this is actually, this happens to be my h t now, which is 2 h 0 t, because it is excited by delta t and I have got y t as this. This must be my impulse response of that whole system, which is this. Okay. So, if I just take it to the frequency domain, so what will be my h f? That must be, so cos I am multiplying, so this is just a frequency translation of this h 0 t, if that is h o f. So, h o f goes to plus f c and minus f c, there will be a half due to that cos, and that half with this 2 gets cancelled, right. So, I get h o f plus f c plus h o f minus f c. So, if my h o was something like this, minus b to b, what is h f? Nothing but this gets translated to plus f c and minus f c. So, this is 0 plus f c minus f c, that is 2 b. How does it look? This is just like a band pass filter. So, therefore, with all these things, what I have created is an ideal band pass filter. So, what was my x? That was within that band, okay, a band pass noise. We were talking about band pass noise. If x is that, because x was actually my band pass noise, if I pass through a band pass filter which is having equivalent band, so this y t will be exactly same as x t, because it will just pass everything. That is already a band limited band pass signal, passing through the same band, it will just give me same thing, nothing extra will be coming out. So, therefore, I can always write that my S y f, what that should be? That should be mod, we have already proven that S y f output should be S x f into mod h f square, right. But my S y f is exactly equivalent to my S x f, right. So, therefore, I can immediately write my y t is nothing but x t. This is something I know already by design. Okay. So, now if I just take back that same thing, okay, so this is now becoming my x t. Now, let us trace back. What is x t? X t is something over here, let us say that is b 1, I call that as x c t, whatever it is, and I call this as x s t. This multiplied by cos and this multiplied by sine added should be, means giving me back x t. So, therefore, I can always write x t as something, I do not know what that is, which is x c t multiplied by cos omega c t according to the design of my overall circuit, and x s t sin omega c t plus theta. This is true for any value of theta. So, even if I put theta equals to 0, it must be still true. So, I can always write therefore, x t is actually nothing but x c t cos omega c t plus x s t sin omega c t, where x c t is nothing but my signal at b 1 and x s t is nothing but my signal at b 2. Now, if you just ask what is this signal? This was after passing through a low pass filter. So, this must be a pass band signal or base band signal. So, it is a low pass equivalent signal and this is also a low pass equivalent signal. So, the band pass signal or band pass noise is nothing but means represented by in phase component and quadrature component, which are just low pass equivalent signal. That is something we have proven right now. So, what we will try to do in the next class is to see the characteristics of those XCT and XST. What are they? Because we already through the circuit we know they also have a relationship. If we just see the other half of the circuit, we will be able to get some relationship between XCT and XT, and from there we will try to characterize what they are, what are their specific properties, we will be able to characterize those things. So, in the next class probably we will try to do that. Okay. Thank you.